Hi, Mike. It seems like it's just the two of us today. So I had a question. Do you want me to go through the notebook or can just discuss any interesting things? And were you able to run the notebook successfully?
Yeah, I ran two of the notebooks successfully. I didn't run the 200 epoch one.
Okay. So in this one, I mean, there's not much that's new and unique other than the transformations that he talks about. For some reason, for me at least, because I'm loading the data on Colab, I had to break it up into chunks and then load it. That itself gave me all kinds of fits. Eventually, I got that part working, but then when I tried to run the notebook, each one of the so do you run it locally? Do you have a GPU local that you run
Yes,
on?
yes, I have
Yeah.
GPU locally. So
What kind of GPU is it you
it's
have?
a pretty old one, 2070 with 8 gigs of VRAM.
Oh, I see. Okay. But this one, anyway, the issue it seemed to me was when I ran it with on Colab, even with the A100, it takes about almost 2 hours to load the data and to run the first epoch. And after that, for some reason, I'll show you what I encountered. That it um, gets interrupted at about 19-20 epochs after the run. And unfortunately, the interrupted thing, basically it loses the connection, it looks like, and I'm not able to kill the run or at least stop that cell from executing. So I get all kinds of internal errors. And basically, if you see, it kind of says transport endpoint is not connected. It loses connection to where the data is stored. And because of that, then it becomes, I can't go in and save the model even after 20 epochs, which is okay because the purpose is just to illustrate that this thing is overfitting. So how long did it take you to execute the 25 epoch runs? Do you
Yeah,
know? Have a rough idea?
it took me around 2 hours. Or
Oh, okay. So
yeah, yeah,
you're able
I
to
ran
finish.
overnight. Yeah.
Oh, I see. Okay. Yeah. So just the other issue with this Colab thing, at least Colab Pro, is you still can't run it continuously. You have to be logged in. So you can see here, for example, that I was expected about 2 hours and 40 minutes, but when about 50 minutes were left of the 2 hours, so it had run already for close to 1 hour and 50 minutes or whatever. But when 49 minutes were left, it got interrupted, which sucked. And I kind of skipped this and tried to run the next one, which is the important run, because that's the one that generates, the code that he uses eventually. But in the next notebook, but that one did the same thing for me as well. And, unfortunately, while it was around 15 epochs, it died. Actually, I tried it separately by running this and then again, tiny custom 25 and it is ran about 15 epochs, came up to this and then died. Again, it got interrupted. So I couldn't ever finish running, which was very frustrating. So no matter, I mean, I was able to load the data and stuff, but it couldn't run at all. So there are some interesting things in this. Obviously, he changes the model. He performs the augmentation, does the random arrays. Primarily, the base model, he figures out that, okay, it's overfitting, as we saw from this chart. It kind of clearly shows the overfitting. Your validation loss flattens while trading loss continues to go down. Even this is not too bad if it continues to, but eventually it kind of begins to climb back up. So that's the reason he says, okay, this clearly shows that, okay, the model needs to be, or actually that augmentation becomes a necessity. You're not getting, you're overfitting. And that's the reason that, and then the other interesting thing which he pointed out is he goes to the image classification on Tiny ImageNet and points out that many of the results here at the top, while it says that there is no extra training data, they're actually using extra training. Almost all of them, even though there are excess here. And so eventually he points out that I think somewhere this best next guy are the only ones where they're not actually using extra data. And so that's what he's kind of trying to compare his own results to. And then obviously he talks about how you go change. So far in ResNet, the only thing he has done is provided the residual connection, but he hasn't done what typical ResNets do, which is duplicate the residual blocks so that there are multiple of them in each chunk, if you will. So that's the n blocks thing that he uses, 3, 2, 2, 1, 1, which means that there are 3 rest blocks. The first part, not just a single rest block, but 3 of them, one behind the other. And the other interesting thing he does in this is to say that you just do the, how we reduce the size as we go through the network, you just reduce the size in the last rest block rather than do that first. So you go through the residual block, but then change the size, which is the stripe 2. So the stripe 2 is the last layer. And then he does this random arrays in order to make, provide some augmentation well to the images. So that complication of the adding the multitude of residual blocks increases the total parameters and the block count. So here you see 21 and 710, whereas I think previous version of it would be 19.7 versus 21, and this is only 303 versus 710. We vastly increase the complexity of our network, and you're also doing augmentation. So you go deeper and you augment more, and that's when you get better results. Eventually he gets it, I think, close to 62, 61 and stuff. So, and the reason he decides that you can go and increase the epochs that you provide to this is because you don't, unfortunately, I don't know why, but it didn't plot the validation plot. But the point is that you're no longer overfitting. And if you're not overfitting, then throwing more epochs at the problem is valid. If you just throw more epochs when you're overfitting, then all you're doing is making the network learn or memorize stuff. And then he points out this is an interesting idea as well as the issues with it, right? He talks about this trivial augment wide augmentation methodology, which is good to know is integrated into PyTorch. What it does, and which is, I think I had not known about this, and also its integration with PyTorch, but it's a really neat capability because basically what it does is you can randomly pick different augmentations versus doing the same augmentation for all the images in the batch, because obviously that's going to make the challenge the network more, forcing it to learn better. And there is, for example, documentation on trivial augment wide. PyTorch has that directly integrated. The other fascinating comment he makes about trivial augment wide, which he does add to the augmentation, as I said, made the network already more complicated, so the model is more complex, but he's also increased the augmentation that he does. He's added trivial augment wide and also added random arrays. But the fascinating thing, there's a couple of things about it. Is this one, he says that it requires having a PIL image, not a tensor. And because of that, you do the augmentation after converting it into RGB and in kind of while the image is still in a Python image library format, if you will. So the augmentation transforms, like these guys, pad, crop, blah, 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 are done in that space. And then you convert to a tensor. And moreover, you norm, and then you apply the erase transform. The reason for that is that you want the random erasure to happen after you have normed, because the random erase uses noise, and you want that noise. It uses distributed Gaussian noise, and that noise is relevant after we have kind of applied normalization. So those are two things which I thought were interesting. The other most interesting thing that he points out is, and this is something else to think about, I guess. I hadn't thought of this at least, so it's very insightful that he points this out, is that if you were to apply this trivial augment wide to an entire batch instead of to every individual image in the batch, which means that applying it at the batch level versus at the individual image level. So the difference there being that if you apply it at the batch level, he says that what I interpret applying it at the batch level to mean is you apply to certain batches trivial augment wide, which means that you do different augmentations, and to other batches you might just be applying the same augmentation to all the images in the batch. But if you do that, then he points out at what I thought was an insightful issue, which is the batches to which you apply trivial augment wide are obviously going to be challenged in terms of the loss. By that, I mean the loss is likely to be higher than if you were to apply the same augmentation to all the images in the batch. So what happens when you're training is that particular batch, the loss might jump up. And when that happens, then you're no longer getting the smooth curve for training that you anticipate. And that can throw you off getting a good results. And because of that, it's important to do the trivial augment wide, not at the batch level, but at a per image level. So I thought that was an interesting kind of thing to keep in mind in general, that if you do something on a per batch basis, you need to be careful, because if you do something which makes the network kind of suddenly for a particular batch behave very differently than the series of batches that it's training on, then you're likely to not get a good result from your training. I hadn't seen that concept or that thought anywhere else. So I thought that was kind of rather insightful. Keep in mind when you're doing. So he doesn't, he goes away from the batch transform and instead does the transforms at the per image level. And then the other thing he talks about, which also is kind of interesting, more because of the uniqueness or the customization that he kind of pays attention to, and that is this pre-activation RESTnet. So he talks about the paper in which they talk about so far. In fact, if I can go back to, I think point is that in the current convolution, that means up to this point, in the convolution that we had set up for the RESTnet, this notebook initially coded our RESTnets. After talking about the skip connection and stuff, he codes the RESTnet. And in this particular RESTnet coding, if you see, we apply the activation after we have joined the ID path and the traditional convolution path. Right? So the activation is applied at the very end. And the second of our convolutions it doesn't have any activation. The reason for this is because you're applying the activation after the two parts have been done. So that's how originally the REST block is coded in our residual network. Now, of course, this REST block is duplicated as we saw in this notebook, but that's just a duplication of this REST block. But underlying this single REST block, the con block that it's made of does not have an activation in the second convolution. And the reason for it is because you eventually combine the activation after you have combined the ID path and the convolution path. And there's a paper which says that this is not the best way to do it because there's, this ID path, there isn't really an ID path because it goes through this activation as well. And that's not preferable compared to an alternative. And what's the alternative? The alternative is, so currently what we're doing is we're doing convolution, we are norming. So remember that this norm is the first norm and the first convolution. And so there is an activation. And then we do the convolution, we do the norm, but there is no activation here until we add the ID path and the convolution path, and then we activate. But that is, and here et al., there's another paper where they point out that that doesn't leave us much of an identity path, and it's better to do the following, which is first norm, do the activation, so you flip the order. So you do norm act convolution. So you can see compared to this guy is norm act convolution. So you've flipped this sequence, the first sequence. And then second one, because you're flipping it again. So in this case, you do norm act convol, and then you add. And so this way of creating a REST block is called a pre-activation. And the pre-activation, I think in me at least, it's called pre-activation because you activate before you go through the convol. Whereas in this case, you activate after. So it's called pre because you're kind of activating before passing through the convolution. So that's the pre-activation REST block. And when you do that, there are a few other things that you have to keep in mind as well, which we'll look at in a minute. But the other interesting thing, and this I thought was the even more interesting thing, because I had seen this pre-activation rest block in a couple of other courses before, but the weird thing he points out is that pre-activation rest blocks actually work worse for fashion MNIST. That's kind of a interesting kind of empirical thing that, things that work at a large scale don't necessarily work at the small scale, which is somewhat counter to what he's kind of pointing out, right? Like, because in his research, he mainly does research on small things, which I think is the best approach, because you can iterate fast and figure out what matters and what doesn't. But this one kind of is interesting because you may have given up on using pre-activation if you first tried it on fashion MNIST, where it doesn't give you the result that you hope for. But then when you apply it at a larger scale, for example, which is what he and his Kai-Ming He and his collaborator figured out that it actually matters for very deep network and for where we have significant augmentation. So it's kind of something also keep in mind, that I guess if you are trying something, then maybe you need to try it at different scales as well to see whether it works or doesn't work or has the same results. But anyway, he does use the pre-activation network and changes the rest block. So that's where you do the norm, you do the act, and then you do the con2d. Right? And then you can see also in this case that the con block, so the underlying con block is changed. So instead of doing the convolution and then doing the norm and the activation in the rest block, here you do the norm act and then the convolve in the con block, and you do the activation in both of the convolution. And because you've done this, there's no activation in the rest block itself. So you can see, compared to the prior, you don't have any act here. So if I were to show you the rest block, here you can see activation of the combination. Here you don't see any activation because that's already happened. So then it's just the con plus the ID con. Right. But then there are, because you have changed the underlying rest block, con block, activation sequences have been changed around and stuff, then you do need an activation and a batch norm after all these blocks are done. Because previously you finished with a norm and an activation, right? But now that's not the case. You start with them. And also you can't start your residual net with a rest block because the rest block, if you start with a rest block, then you would have an activation immediately. And when you do that, and you have to keep in mind that as soon as if you activate right away before you norm, or even after norm you activate, then you're throwing away half of your inputs, right? Because if it's a value, any kind of a value thing, all the negative values go away. So that's something else to keep in mind. So that's the reason that the first layer is a con2d layer as opposed to a rest block layer. That's one change in the rest block in actually getting in the model creation. And this is one change from what we had before. And then the other change is the fact that because we are doing in all of these small rest blocks, that is the duplicated capital rest blocks, we now have to do the activation and the norming after all of these blocks. So previously we had the norming and the activation, right? And now it's previously it was at the end, and now it's at the beginning. And because of that, you have to do the have to. And so after you make all those changes, and then each augmentation images are shared, blah blah blah, but you do it at the image level for the reason that I was telling you earlier, that you don't want to do it at the batch level. And then he fits and he gets the results all the way up to 65%. Interestingly enough, he doesn't care to use this in his next notebook. And I had a question as to how the next notebook worked for you, because there was something there that I observed which at least doesn't make sense to me. Now, because I was unable to run this notebook, I obviously couldn't import a model from here onto the next notebook. But I had a question for you, which, as to how you were able to run this, unless, there were some modifications that you made. So in this notebook, the idea he has is to do this super resolution. And so basically he's trying to improve the network. In fact, I don't know whether you followed his earlier courses, but there are earlier lessons which I'll post a link to, where I think he gets into what I prefer this particular stuff. But there is an important reason why it's important for us to go through this notebook, because units begin to make an appearance here. And if you haven't gotten familiar with units, then it's the first time that units begin to. But this is a earlier version of his course where he also talks about super resolution and image segmentation. This is an interesting, because I have gone through this notebook when he taught it. It might even use the first FastAI version, which means you'll need to modify the code to run it. The current FastAI, and even more with the mini AI. But regardless, it gives a good explanation for much of the techniques that uses in this notebook. So anyway, he just first shrinks the image to 32 by 32, and then just duplicates it to 64 by 64, because all he says is, well, I just want 64 by 64 input and 64 by 64 output to keep things simple. But I'm going to do some random arrays in order to challenge them. Rest of it is kind of fairly similar. He first tries it with an autoencoder, giving all these, and so upsampling in this case is he just uses a doubling in the rest block. So he just undoes a stride of 2, whereby you bring the size down, and instead you just increase the size. And then the other interesting thing he points out is obviously why we do a stride 2 and shrink size, the HNW, why we shrink as we go through the want to force the model to learn abstractions, which it wouldn't do as good a job if we kept it as. And then it compares the results, right? Like the input images have low resolution because we have taken a 64 by 64, taken it down to 32 by 32, and then just duplicated the images. So obviously duplicated the pixels. So obviously that's going to be chunky and bad. So that's what this input is. And then with the autoencoder, the predicted images are pretty horrible. And then he kind of goes through and explains the architecture or structure of a unit, the down path and the up path. And then in the original paper, they didn't use residual nets. In the up path, they just use con nets, but the idea remains the same. By the way, in his prior lectures as well, he kind of comes up with, I don't think he uses that here because his goal is to go through a stable diffusion. But in this case, what he, or in his prior lecture, what I thought he had done, which was also, intend to go back and revisit that lecture because one of the things he did there, which I thought was very interesting, was provide a parameterizable unit. That means depending on the image, that means you can kind of provide some parameters to the unit that he created, which enables you to deal with images of varying sizes, rather than it being kind of fixed to the image size. And then obviously the idea here is to copy it forward and then use half of the image from the prior values you save in the down path, combine it, and the combination can either be a concatenation or an add. For super resolution, he says that addition is probably makes more sense, but that's for other applications like segmentation and stuff, they concatenate more often than add. But I've seen it done both ways. And you concatenate or add, and then you kind of convolve in the results that you seek. But the other interesting thing he does, which I haven't seen in any other implementation of unit, although I haven't looked at a unit TIM implementation, I don't know whether you have mine, is he actually, besides the forward path here, the first thing he does is to take the actual input X and directly feed it in, rather than just after the two convolves. I'll show you that in code in a minute. And then eventually towards the end, he also talks about one other modification that he does. That modification, I think, has become more common nowadays, but at least this directly using the X input is not something that I've seen done before. Anyway, so, he gets the results, he begins to implement it. The downsampling path is a bunch of rest blocks, and he uses that as a module list. And a module list is not the same as sequential. You have to kind of then pass through each of this, rather than in sequential where it automatically goes through, if you will. Then, so you have to do things like X equals cell of X, which you will see in the code in the forward. And then the up section is just the up blocks. And then finally, you go through one rest block in order to convert from how many ever channels you have to the 3 channels that you need. And this end is the thing that I was rambling about earlier, where he takes the X input and directly combines it with the results of the up block, and you pass that through another rest block. So at that point, because the input is also 3 channel, you can add the 3 channel, and your size of the output, because of what you have done, and your objective is to get it back to the same size as X. So at this point, you're just kind of using a rest block to combine the actual input image and the output of the unit that you got. Here, that's activating through an identity and just norming it. So you'll see, I think, in this notebook, or at least in the next notebooks, you'll see different ways by which he does this forward path saving. That is, you save on the down path and how you forward it when you need the activation during the up path. So in this case, he just saves it in something called layers. He appends. Now remember, because we need directly the X input itself, that's the end rest block usage, he kind of saves the input. So in layers, he just appends X. Then you go through the thing called start, which is this initial rest block. And then you go through the down path, because it's a module list you have to do for each layer in this down. You go through layers.append of X. That means you take the X input and append it after every level of going through it, and then you also pass X through the layer. You save it and then you pass it through. Then you kind of keep track of the number of layers you pass through, because you'll need to remember that in order to utilize the appropriate output when you go up on the up path. And so you then do the enumerate. And if it is not zero, the reason it's not because you don't do the combination in this last pair. So as you're climbing, the very first step in your up path doesn't have this forward arrow. So that's the reason that you have this I not equal to 0, x plus equals layers n minus I, which means for everything but the first step, you have to combine the layers. That is from the down path and the generated up path, you concatenate it, which is what you do. Excuse me. Here he doesn't concatenate, he just adds. And so that's why it's x plus equals layers n minus I. If you were concatenating, then obviously you do this differently. It wouldn't be an x, you would kind of look at a stack or do things like that. And then the end thing I told you that he does, which is different than what I've seen before in units, is he also then add the layer 0, which is the very first x that you've saved. Okay? Layers.append x is the layer 0. So that means this is the input and this is the output from the unit that you've gotten, and you pass that through the final rest block. And there's a lot of commented code, so you kind of vertical space is challenge. Instead, you can see the whole code here of the basics of the unit. So I thought that this is fairly dense code, but very succinctly and insightfully coded.
Yeah, it's a very small version for what it's trying to do.
That's pretty impressive to keep in our back pocket when do. Then he also, this is another interesting thing, is he defines the 0 weights, right? And so kind of works through what would we like to do or what would we want the network to behave as we begin to train it. And so he says, look, initially when we start to train, obviously our up path is going to be, well, the whole network is going to be untrained, but in particular, the up path is going to get all static. It's not trained at all. So then what we would like ideally for the network at that stage to return is pretty much the input, because we have this input coming into us. And if we want that, then we would just zero out the weights of the upcoming path, right? Because that's not yet trained. So he says, let's just zero out the very last convolution in the ID connection. So in this last thing we see, x plus layer 0, just make, x, just zero out the x, right? Because then it will be layer 0, and layer 0 is nothing but the input x, whereas this x is the output x, if you will. And so when you do that, then pretty much you'll be returning the input, which, in a super resolution context and stuff is what you want, because you want the input image to reappear, at least as a starting point. So in the equation, this x will be 0, so the self.n will get layer 0 as input. We also then want to make sure that self.n does not change anything, right? So, and there's some other variation you can try. Should it be set to an identity matrix? That's not what he does here. What he does here is he just zeroes out the weights of the last ID con, the end con, and the last resolution, last rest block. And then he trains using, the weights and stuff. And he kind of checks what the images look like. These are the input images. Now remember that the reason they are this way unchunked is because you've kind of shrunk them to 32 by 32 and get it so to get the 64 by 60 size. The outputs, if you look at now, they are a little better. They are not as horrible as the autoencoder outputs were, but you still see that there's a big difference between the original and this guy. Although the outputs begin to be a little bit closer to our inputs, they're not as horrible looking as the autoencoder outputs, which you see here. You can barely recognize that. You can see that we have significant input, but that, it's not shocking. You've kind of provided parts directly from input to output and pretty much and so on. So that's not shocking, but it also shows there's still work to be done because it's not as great compared to the original. Right, so you can look at the collar's eyes in the original. You can see the eyes. If you see here, there's nothing. If you see even the eyes of the kid here versus here, you can see the eyeballs. You can't see it. It's not that great. So then he goes through, the idea of using. So far, we've been using MSE, and MSE has this ability to kind of smoothen the images because you're using average values of pixels in local regions and stuff. But we've already seen when we did this style transfer that it's much better if we can actually use perceptual loss, right? Which means you take certain slices of a well-trained classifier, for example, and then you make sure that your layers compare at the appropriate point. So this is where he uses the model trained from the notebook, and because I wasn't able to train, I can't do this. He uses the iNet Tiny Custom 25 model for it, and he kind of does the same code as before, blah, 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 just use the C model, which is our reference model, the classifier model, and then he just decides when to lop off that classifier model or which layer to use the output from in order to compare the values from our unit and the classifier. And now this is where I had a question for you, Mayank, because this notebook would simply not work even if I had successfully trained the model, because in this case, he's loading learn.model.load this super resolution cross pickle model, but he hasn't yet trained this model, and at least I couldn't find this model in the model source. So how did you get past that, or how did it work for you?
Yeah, I've just commented out this.
But if you comment out this part, which is you're loading the cross pickle model into learn.model, right? Then your learn.model right now is, you just used, I guess, the model that was trained until this point, which is the unit model trained to this particular point. Is that what you're doing then by commenting out this particular line?
Yeah, I've commented out that particular line, but I have not specifically added a learner to the C model here. So the C model here takes it from the above, which is the iNet Tiny Custom 25.
That it's already using the iNet, but what it's comparing to would be the learn.model. But that means your learn.model at this point, if you comment out this line, would be the model that you've trained up to this point, right?
Okay.
Which would be the unit model that you've used and trained to this point, which is this unit 20 epoch trained model, right? Okay, so that at least makes sense. But I was like, wait, if you do this, there is no way that the notebook would run, because there's no, I mean, eventually down in the notebook, he creates this model and saves it, but you can't load a model before you save it. So, okay, that's interesting. Oh, one other request: if you have successfully trained the INET25 model, can you provide a link to it on some shared drive or something, so at least I can use that and see whether my notebook runs, this notebook runs, because then I will have the weights and stuff from that model that I could potentially download, like a tiny, INET tiny custom 25.
Custom 25, yeah.
If you can provide the pickle version or whatever of it, that would be great, because that will help me run through this notebook. Because right now, I can't. So you kind of grab.
Yeah.
Sorry, go ahead.
It's 85 MBs and I can share it in a drive or something like that.
Yeah.
Cool. I will share it and put it in the Slack.
Yeah, that'd be great. Because I'm stuck otherwise. Okay, so then he goes through and kind of makes sure that he compares, and he says, hey, let's start off by saying at least the signs should be the same. And then let's kind of use the MSE loss along the way between the features and the predicted features. So this is where, for example, the predicted features is, one of them would be from our reference model, that's this classification model, and another would be from the unit model that we are training. And then you combine the losses. So you take the target features are the classified models, and then the feature loss, which is MSE loss between the input features and the target features. And then you combine the feature loss, but then the scale sometimes isn't the same. So you kind of empirically figures out, you divide by 10. And I think John chimed in that this divide by 10 seems to be fairly common. And so you do the feature loss by 10 just for scaling purposes to keep the loss, keep both losses in proportion. And then you do the MSE loss as normal. So you combine the feature loss with the normal MSE loss and get the unit, and you do that. And he shows that that's even better than before. So this is again the inputs. Our outputs begin to see vaguely the eyes beginning, if you can squint. And this, at least the image of this kid, is you can begin to see the eyeballs. I think getting immediately to the previous version, right? This is the original, but you can see this is our, you can't see any eyeballs here. When we did it just with MSE loss, but with this feature loss combined with MSE loss, where you're using the classifier to kind of take certain nodes in the network, you see our outputs, you can begin to see the eyeballs. Not great, not as good as this guy, which is the original, but still much better than before, right? So, and then his point is that, one could think, hey, why can't we use FID and see whether this output is better than what we had before when we just used MSE loss? And he says, well, we can't do that because, looking at images is the only answer, because if we did, then it would only focus on percentiles and stuff. And then this is, I thought, a very interesting idea as well, where, and it's, I think, to his credit, he has always done this in fast AI courses, which is periodically or sequentially unfreeze layers in the network, right? So that's the thing he's doing here. And even more clever, I think, very, very interestingly, what he says is, look, instead of going through and training my down path as I do this resolution, what I'm going to do is I already have a well-trained classifier, which you can think of as just, or in fact, in many ways is identical to the down path of this unit network. So our classifier is pretty much, you can think of our classifier as, forget this up path, just load, just replace the head, get rid of all this and put a head here, going down to whatever the number, 200 outputs or whatever. And that will give us our iNet tiny custom 25 or whatever. So if that's the case, then why not take all the pre-trained weights from that classifier and shove it into the down path and train the up path for just one epoch. So that very quickly puts this, I tend to think of it conceptually as almost applying initialization, but very smart initialization to the up path values. I thought that was an incredibly interesting thing he did, because he just takes the weights from the classifier, you can think of the classifier as just the down path, and shove it into here and do one epoch run and then unfreeze everything. And while you're doing this, you freeze the down path. So you're not training the down path anymore. You just take the classifier weight, shove it into this, and just allow the output, or sorry, just allow the up path weights to be trained for just one epoch. To me, that almost seems like you're just initializing the entire sequence of the up path with some good values of the down path, right? Because the down path is identical to the classifier. By the way, Mike, you had posted or questioned me on like where you were getting error. Did that error go away, or were there some issues with what you were trying, or is that because of that single line of code that was there, or what? I mean,
Yeah, there is an error. It hadn't gone away. And yeah, there is a problem with the training of the perception loss using iNet Tiny Custom 2025. So there was
so,
an error. Yeah.
so you weren't able to run this notebook successfully then?
Uh, it kind of ran, but the error still persists here. The loss rate is not like he had, and the loss rate is like, let me try to share my notebook. You will get that.
I'm sorry?
Let me try to share my
You want to
notebook.
share?
Yeah.
Okay. Yeah, I'll stop sharing.
Can you see my notebook?
Yes.
So this is the error log that I had. It's not going down as it's supposed to. But
Where do you see the first error that you observed? And it's kind of weird for that particular chart that you show where the validation loss is lower than the training loss. So that itself is kind of strange. But anyway, let's take it step by step. This one, when you load the P model and you're trying to load the static then it tells you that there is. Yeah, see, this one, what I was thinking of is it because the model is not identical and he has changed the model between the tiny custom 25, loading the state dict from the tiny 25 to the unit model will only work if the down path is identical to if the unit down path is identical to the classifier path. And what you see here, in fact, when it complains, is that so you see this the size difference. So it seems like in the unit, the first layer, I don't know in which one, but the two networks aren't same. Because in one case, and I think that's the, classifier, we are doing a 5 by 5 initially, whereas the unit seems to have a 3 by 3. And that won't work, right? Because you now are not loading the same values. So that seems to be the problem. So one or the other has to change if this method is to work. So I don't know whether he originally had both with the same or what, but that seems to be the problem.
Yes, so
right? Because if you see, everything else is same. So the model is not identical.
Yeah.
That's the problem.
The model cannot be loaded here, so I guess that's why I had this weird graph that I had.
Yeah. So that's not actually working. So I think one or the other has to change to be either the 5 by 5 has to become a 3 by 3 or the, which means that either, and, that kind of flips the whole thing back again, right? Like, because if we are better off changing the unit, at least right now, even though that may not be the correct thing to do, just because otherwise you'll have to retrain the classifier, go through the 2.5 hour training session again.
Yes.
I think it's the classifier which has a 5 by 5 input. And if that's the case, then you'll have to make the unit a 5 by 5 input to start off, which I don't think it is currently. So if, you can go back and check. Yeah, see, that's a 5 by 5, right? For the classifier model. But if you go back and look at the unit, then I bet you the unit is a 3 by 3. Yep.
I think so. This is the one.
Yeah, right. Yeah. See, here it's first start thing is
Yeah,
3 by
that's
3.
3 by 3. Yeah. Second.
So we need to make that a 5 by 5. I don't know whether that's a smart thing, but at least for the perceptual loss to work out a problem. So then you can load the weights one to the other without getting that error.
Yeah, I will try to add a case here and make it 5 by 5.
Now, where is the, just so I can figure out, so where is the thing that it's a 3 by 3? The input is 3, but how do we know that it's a 3 by 3? Kernel size default is 3. Is that the reason?
Yes, default is 3.
Okay,
Here,
yes, in 3.
you can
Okay,
see
yeah,
here in it
yeah,
as
yeah,
3.
yeah. That's the problem. Why you wouldn't? Why you were seeing that error?
Mm-hmm.
Okay, so back to what, and then there's just one additional thing that he does. Thanks for sharing that. The last thing he does, which I thought was also interesting because I haven't seen, although we'll see in the next lecture or two whether that's common in the stable diffusion world of UNet implementation. But you know, as I mentioned, right, you see that the original, you can clearly see the eyeballs, but in our thing, it's kind of still fuzzy. I mean, you can begin to see the eyeballs, but it's not that great. And you can actually, in the koala, especially, you can see the eyes, but you can't see the eyes in our koala. So what he does, right, is besides using the perceptual loss makes it a little better. So you can kind of see but even here you can't, I mean, you can kind of squint and imagine an eye, but it's not that great. And again, the kid's eyes are not as great as the original that you can see. You can just go look up and look here. It's good. It's beginning to get really good, but it's not as great as this, right? So the thing he does is what I just talked about, which is preload the weights from the classifier into the down path. Train for one epoch. So do not start with fine-tuning the whole thing, because at the start it's going to be crap. Just start by training the random weights of the up path for at least one epoch, with the down path using pre-trained frozen weights. Right? Which means you use the classifier weights, shove them into the down path, freeze the down path because you don't want those weights to be tuned. Then train the up path, or in my mind, basically you're just, that's why I said I think of this as a good initialization of the up path, because all you're doing it is for one epoch, one or two epochs. Then unfreeze everything and start from those set of weights, and then train the whole neural network for about 20 epochs. I thought that's a very clever kind of idea, if you will. And then he kind of talks about why it's cheating or not cheating and stuff. But then that's the model, super resolution, whatever, PC. And you can see, there's the input, there's the output, and there's the original. And you can, again, see that it's slightly better before. Right? And then the really interesting idea is on top of it. This is where he talks about the dual purposes of the UNet down path. By that, if we look at, sorry about scrolling, but if you look at the UNet, so one of the things that he talks about, and again, I don't remember that this was stressed in the earlier versions of its course, but I guess people have learned about this as they continue to use the UNet, is the fact that the UNet down path does two things, right? One, it shrinks in the forward direction, it kind of shrinks the image. So that's the red arrow, right? The max pull 2 by 2, strike 2, whatever, kind of generates the output for the next stage in the network on the down path. But it also is creating, through the saved layers and stuff, the output that goes into the up path, right? So it has kind of two outputs, one output, which is the saved output going in the forward direction to the up path, and the other output going in the feeding forward into the next step of the down path. And he says that those are kind of two different purposes. One is to generate this output, the other is to generate this saved output. And it would be better if these two purposes were separated. And the way to do that is to put in a resolution ref block on this direction. And so you kind of separate out the purpose for the gray arrows from the purpose for the red arrows, which is the final improvement he does besides the perceptual loss, besides the initialization of the down path with the classifiers weights and training the up path while freezing the down path for a couple of epochs, then unfreezing the whole network and training. On top of that, he does this cross, what he calls the cross connections. Or is it cross? Yeah, so this is the two different purposes I talked about, one for the down convolve and another to feed forward. And so add some ref blocks in the feed forward. They're called cross connections. Yeah, they are called cross connections. So the cross convolve is going to be a ref block followed by a convolve. So you kind of define a cross convolve, which is basically a ref block in the beginning where there is an activation, and then you do a convolution where you don't change number of filters. And you change the unit to add the cross convolves. It's these two lines of code. And obviously here you are now adding the output of the cross convolved layers saved output. So you take the output, which you're getting from the down path, this unit, save this, but then when you're using it, pass it through the cross convolve path, use the output of that and add it to the values that you're getting through the green arrow, right? And that gives us even better results than before, as he shows with pictures. So this is the cross convolve idea. Kind of do that. And so if you look at the original code is this, right? You just add the layers. But now because there is the cross convolve path, right? You do self.access I, which means the output of the cross convolve, and what you send to the cross convolve of the ith layer is the layers n minus I, right? And then he doesn't do this here, but he says that actually one of the things he missed is, remember that he also does the, different than any other unit is he combines the very input to the output of the unit. And he says that actually it would have been great if we added a cross convolve to the layer 0 and then added it to X. So these are a few other things that you can play with in this model to see whether you get even better results than before. And then that's where he uses the P model. Actually, and I noticed that he has, for the start, introduced KS equal to 5. So I am somewhat surprised why you still see 3x3 in your case. See what I'm saying? This KS has been modified to 5. So when you
So
do the dot load inet 10 a custom 25, then it should be a 5, right? Or because the unit is now a 5. That's the thing we were thinking that you would need to modify to a 5, right? But it's already a 5.
it's
I'm
this
confused.
this code is for the cross convol part, right?
Right.
And
But
that
yeah,
that
that's
was
correct.
for
Oh, when you did it previously, maybe he doesn't have the KS equal to 5. So you just need uh, this line to be copied over to the prior tiny unit. Is that the issue? Yeah, see, here he doesn't have that. If you replace the self start of the cross convol thing here, then I think you should be fine.
okay. I will try that.
Okay, and that after you do that, you get the unit, do that, train it, 20 epochs, 15 epochs even. You can see that, this is the input, this is the output, and the original is that. So you can see somewhat better, although I'm not convinced that it's a whole lot better, but you can see the eye of the koala for sure.
Hmm.
In this case, you can begin to see a clear eye, though the kid doesn't look all that much better. The original and this, but at least on the path of improvement. And he suggests various kind of tricks that you can use or things to do with this whole super resolution kind of technique. Removing, I definitely plan to play with this. One of the things that maybe you guys are already aware, but one of the things that one of his past AI students has done a lot of work on is colorizing images using this super resolution technique. And he's going to produce some outstanding results, even as an application, I think. Colorizing black and white images. That's very cool because you can use, like old photographs of weddings and things like that, and you can train the network on some Indian weddings or some other wedding things. If you have wedding pictures, or if you have like, tourism related things, you can train it on a bunch of current tourism images or current weddings, and then throw the black and white images at the converter, and it gives you a pretty good output image of the original black and white images in color. I've seen it work, which is pretty amazing. And then he talks about this is also interesting, right? You can kind of force it to create a panoramic image from multiple images that you've taken in that. Or you can make it create a painting from a drawing, stuff like that.
Okay.
So kind of frustrating to me because I wasn't able to train it, and therefore I was limited in what I could do with this. So after you get the thing checked out, if you can dump the weights, that would be awesome, because then at least I can run this notebook and play with it, even if I can't train the network myself.
Okay.
Okay, any questions? All right, we just have 2 more lectures to go, and I think in the next lecture, he kind of pretty much takes this unit and modifies it and applies, the keras and the other things to it. I think the next lecture, he pretty much takes it from zero all the way up to stable diffusion without using latents, which I think is pretty fascinating that in one lecture he's able to do that. So that's that, and we'll have one more lecture after that and we'll be done. Thanks for joining. See you all next week.
Okay,
Thank you.
take care.